All right, here was the homework that we had yesterday in the book. We do have. Let's get started here, please. We do have a quiz tomorrow over sections 1, 2, and 3. Let's just kind of go through and kind of summarize the things that we've had up to this point. A little bit of new to look at today, some problems, but go back and make sure we can kind of organize our thoughts on all the things and where we've come to this point. First of all, in section 5.1, okay, in section 5.1 is where we first encountered the idea of the definite integral, an area. So we had this idea of a definite integral, and meaning, and we've been doing so much work for about 3 days on this thing called the area function that we kind of forget where we started with this whole notation, and that was this idea that you have the integral from a to b, f of x dx, right? That thing is called the definite integral. It's a number. It's just a fixed piece of area. It's like f prime of 3 is a number. It's a slope at 3. There's a variety of ways to find the slope at 3, right? We learned, of course, in the end, we learned these derivative rules, and so that's the best way, do the derivative, plug in a 3. But we also, if we didn't have an equation, we could graph a line, and we could draw a tangent line, and we could estimate the slope that way, or we could pick 2 points really close together and estimate the slope that way, right? We had a variety of ways you can find f prime 3. Maybe I give you an f prime graph, and you just look at the output at 3, and that would be f prime 3, right? So f prime of 3 is just a number, and we had a variety of ways of getting that. The most common one, of course, was do the derivative, plug in a 3, okay? Well, definite integral is kind of the same thing. That just represents a fixed piece of area. It's a number. There's 3 ways, typically, that we can do area. Okay, the first one we looked at would have been geometry. So in your in section 1, we had somewhere they just gave you a picture. It was triangles, and I think I even have that one up here somewhere. One of those. Let's see.
Since you wouldn't have closed it.
What's that? Well, what's funny is my computer just kind of crashed on me. Imagine that with all the open windows and
I wonder how that could have happened.
all the open things I had going. So I did lose those things. So here we go. So I might just give you a graph like this and ask you for the area from here to here. Well, you got half circles and triangles and trapezoids, and you can just use geometry to find that area. Okay, but as we know, most functions don't look like that. Most functions, look something more like this. And how are we going to find, that blue area? Well, there's no geometric formula for that. Okay, so another thing that we could do to find area would be approximation. Now, this was the first thing we did early in the year. You remember where we counted squares? I was thinking about having somebody else run this for me, but I don't know, after last time when Ryan was running it. I don't know. Somebody had, I thought you did a fine job, but a couple people who were gone watched the video. Yeah, they were watching the video. They said, that video could have been about half as long, except we kept waiting for whoever to punch the right button. Geez, you got a video and you're going to complain.
I thought it was funny.
So you were gone. Yeah,
Yeah.
Tori was not the one that complained. It was not anybody in this one. And they weren't really complaining. They commented. So yeah, here you go. Yeah, absolutely. See what you get. All right. So approximation was the first. When we looked at these, we remember counting squares, right? We just count squares and kind of estimate. And actually, the last part of chapter 5 and all of chapter 6 is going to investigate this idea of approximation more. Okay, we're going to get into being more exact with that approximation rather than just counting squares. Because remember, the third way we have of doing it involves the antiderivative. Of course, that's what we ended up learning once we got into section 2 and now into section 3. We left off with that yesterday, and we're gonna pick back up on that today. But antiderivative, well, I think I mentioned this, not all functions have antiderivatives. So therefore, not all the time can we use that to find areas. And not all the time can we use geometry. So we do have to have approximation techniques. Okay? So that will not, however, be on the quiz. There won't be any approximating that you have to do on the quiz. It's kind of like that midterm problem where a lot of you looked at the graph and kind of estimated what the value was, and really what you should have done is you knew it was a line, you should have looked at the slope, and you could have found exactly what that point was. On this quiz, if there's any areas, you'll be able to find them exactly, either through geometry or through the thing we learned yesterday, which we'll write down right now. That was a fundamental theorem part 2, and that was this f of b minus f of a. Right? Big F meaning the antiderivative. So the result we came up with right at the end of the period yesterday was that to find a definite integral, we can just do the antiderivative of little f, plug in a b, plug in an a, subtract them, and that will give us our answer. Now, unfortunately, that only works if you can do the antiderivative. Sometimes you can't. Sometimes geometry doesn't work. So approximation might be necessary, but not for right now. We'll investigate that later. Okay, so any areas you need to find tomorrow, you're going to be able to do either geometry or this thing with the antiderivative. So we'll come back to that. Technically, this would be more a 5.3 thing, but because that's what we just did yesterday. But it falls under the heading of doing a definite integral. Now, another thing that we need to be able to do from section 1, the other thing, there were several things in there. We talked about some of those properties, how you can split apart an integral, you can pull a constant out in front, those kind of things. So those things are pretty basic, I think. I think everybody's okay with those, but don't forget about those. You might want to go back and look at some of that homework, brush up on those a little bit. But the one that we haven't done much with, that you better write down and you better work on kind of memorizing this was average value of f of x. Average value of a function. That formula is average value equals the integral from a to b of f of x dx over b minus a. We need to know that formula. If a problem asks for the average value of a function, and we'll do an example of that here in a little bit, then we need to be able to do this formula. Now, basically, it's just an application of definite integrals. So, if you're finding average value of a function, to do the top part, you need to be able to do the definite integral. Well, how are you going to do it? Well, it depends. If it's a problem where you use geometry, use geometry. If it's a problem where you can do an antiderivative, do an antiderivative. Okay? But use one of these ways to find the definite integral. Divide by that, you have average value. So we'll get to an example of that here in a little bit. All right, section 5.2 then. Section 5.2 was all about the area function. So we said, all right, we got this piece of area that we can find. What about if we took that right endpoint and moved it from place to place and got new areas at every one of those right endpoints and made that a function, called the area function. Okay, so we did all this investigating and Yahoo, Waha, blah, 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 the great big deal, I know, I was very excited, and everybody was like, yeah, wow, okay. And the area function was what? The antiderivative, right? Yes.
I wasn't like that.
You weren't like, okay, all right, thank you. But that was the result. I mean, that was all that, there's a lot of stuff, a lot of notation, all that stuff, but the big deal is it's the antiderivative. Now, here's how we wrote it. And this, hang on here a second. This was fundamental theorem, part 1. Okay, so fundamental theorem, part 1, basically says what we just said in those words, that the area function is the antiderivative. Okay, and it looks like this. Area function little f of t dt. We talked about how you need to have that dummy variable, that t variable in there is just kind of so we don't use x for more than one thing. The x is the real input here. X is the real input there of that area function. And if I do the derivative of that antiderivative, what do I end up with? Little f of x, not t, right? Because it's with respect to x. X is a variable. Basically, you're saying do the derivative and the antiderivative, they undo each other. But this sentence, this thing right here is basically saying that the area function is the antiderivative of little f. That's how you say it. Okay? Now, we did a couple of, well, we did really three main kinds of problems with that result of the area function. All right? The three kinds of problems we did were this. One was, okay, what if I give you this? Derivative of 3 to x, what was the one I used the other day? Sine of e to the 4t dt. That would equal what? That was one problem we said would probably be on it. Direct result of the fundamental theorem part 1. If you look at this, what do you got? Sine of e to the 4x. This will probably be a 1-point problem. If you have a t in there, you don't get the point. If you try to do the, some people will try to do the antiderivative of this. I usually pick one. This actually does not have an antiderivative. You cannot do an antiderivative of this. Okay? Some people try to do an antiderivative of that. But it doesn't matter. This in the brackets represents the antiderivative, and then the derivative would undo it anyway. So there's no need to do the antiderivative. The derivative undoes it. There's no plus c. Somebody asked about that the other day. What about the plus c? Well, when you do the antiderivative, yes, there'd be a plus c, but when you do the derivative, the plus c would go away. So that's why there's nothing on there. And so that's a direct result of the fundamental theorem. Another thing that we did with area function problems was something like this. Let's say we define big F of x to equal the integral from 4 to x of little f of t dt. Wait, time out. Let's don't put little f of t in there. Let's put actual function in there. Okay, so let's say we did the integral. Say we did the integral from 4 to x of 2t minus 1 dt. And I said, and I asked you to find a formula for big F of x. So if I ask you to find a formula for big F of x, what would you do? Do the antiderivative. Now somebody in the other class said draw the picture. Yes, on number 21 and number 29, we did draw a picture of this. It made a trapezoid. We went through that whole long process. I said you won't have to do that on the quiz, right? The basic thing we learned there is, hey, it's the antiderivative. The area function is the antiderivative. But for now, you know that. So here you would just do the antiderivative. So what's the antiderivative of that? Oh, careful. Because remember, it would be in terms of x. So it would be x squared minus x plus some c. It's the antiderivative of that, but it would be in terms of x. Again, the t is just a dummy variable we put in there, so we're not using x for more than one thing. But if you remember, when we did those pictures and did those trapezoids, our answers came out as x's, not t. Okay, so very important that you do that. All right. Now, how could we find the c? We've got this initial condition here that we know big F of 4 is 0. If you put a 4 right there for x, the area from 4 to 4 is 0. So now you put a 4 in here, you get 16 minus 4 plus c equals 0. So 12 plus c equals 0. C equals negative 12, and then you can plug that right back into there, and there's your formula for big F. So that's another thing we did, another result of this area function, and knowing it's the antiderivative. And then, of course, the third thing was the chart questions. And that'll be a big part of the quiz as well. Problems 1 through 8 today, 35 through 38 today, 51 through 56 on today's, what you worked on yesterday. There'll be a few more of those in your homework today. Okay? And I don't care if you talk about it in terms of area or you talk about it in terms of slope, right? I don't care on the justification. Do both to cover yourself, whatever. Okay? All right, so those are the things that we had there. Now let's look at, oops.
Undo.
Oh. I didn't want to do that either. Hey, Ryan, you want to word this for me?
Why is it one pixel at a time?
Holy cow.
Isn't there a button like right below that? Like that blue? Yeah. 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 Not that blue.
I think you might be right.
It's broken. You used it too much. You cannot undo.
I must not be able to undo when I use that thing. Oh well. Well, it was there.
Wait, what?
What?
You hit new slide.
But the line should.
Well, that should be just a new page.
What?
It's a line.
What's going on?
Oh no. I
I
just updated this software yesterday. It just crashed.
Uh-huh.
Oh, man. This
How did that happen?
attempt to recover. Yeah, let's see what it recovers.
Just the line.
Just the line.
Ah,
Hey.
nice. Oh, wait, only that much of it.
Well, you're not missing much.
Oh,
None of them have you click on. Oh, well, then you're missing.
Did you just
Okay.
yourself?
I think.
Maybe just rewind. They can rewind it and pause it.
Yes, absolutely. So, all right. Section 5.3 was the last bit of this. We just kind of got into it a little bit, but this is essentially what we found out right at the end. And the key to section 5.3 is going to be the fundamental theorem, part 2. Okay, and that's what we're going to focus on a little bit more today. Okay, fundamental theorem, part 2. That's what we discovered when we did 61 through 64. And what we discovered is that if you have a definite integral from a to b, f of x dx, that is equal to big F of b minus big F of a. Okay? Which gives us a very nice way to calculate an area. All right? Now, like I had up here earlier, that's one of 3 ways we can calculate area. This only works if you have the equation of the function, and it only works if it has an antiderivative. Okay? Some functions don't have antiderivatives. That's where approximation comes in. Of course, that's not going to be a focus tomorrow. If you have just a graph and it's got geometric shapes, then you can do area that way. But this is one way to do an area. It involves antiderivatives. Okay? And that's pretty much all that section 5.3 has in it. I mean, the homework has some other stuff from 5.2, some area function stuff and chart stuff and some more of those kind of problems. But the only real other thing to talk about in section 5.3 is this right here. So let's go ahead and do a few examples of that. Let's say we have this function right here or this integral from 1 to 3 of x squared minus 3 dx. Let's say we had that integral and you were supposed to just find that area. Now, the directions here would be evaluate, probably, because that's just a number. That's just finding its value. So the direction would be evaluate this integral. They might say use the fundamental theorem, which we'd be talking about part 2, okay? So it says use the fundamental theorem to evaluate this integral. They're talking about this f of b minus f of a thing. You don't have to draw a picture on these, okay? I'm going to draw a picture just to help us, have an understanding of what that is. We're not using the calculators on your homework. If you want to use the calculator to check the answer, there's a template in there to do integrals. So you just fill in the gaps and fill in the bits and you check your answers. This would be a parabola shifted down 3. So therefore, I believe it would cross where at plus or minus radical 3. That'd be root 3 right there. So 1 would be right in here somewhere. 3 would be over here somewhere. So the area we're talking about would be this area. We'd be looking at that area right there. The area from 1 to 3. A little bit of negative plus a bunch of positive. Okay, so we'd expect it to be, but that's not, there's no geometry we can do there because that's a curve, and so those aren't triangles, those aren't anything we can do a geometric formula. So according to the fundamental theorem, we do what? Do the antiderivative, big F. Now here's the notation I want you to use. I didn't show you this yesterday, but the notation I want you to use we're going to call right bracket notation. We do the antiderivative. So what's the antiderivative of x squared? 1/3 x cubed minus 3x. Now, normally you would stick on a plus c, right? You would put a plus c on there. Now, however, if we put a plus c on that, then we plug in a b and plug in an a. In other words, we plug in a 3 for x, plug in a 1 for x, and subtract, and what happens to the c's? They would subtract out. They would disappear. So in the fundamental theorem part 2, when you do the antiderivative, it is not necessary to put on the plus c. It'll just subtract out anyway. All right, then we're going to put a right bracket like this, and we're going to put on the 1 and the 3. Now, the reason I think that is important, now I'm not going to necessarily grade the fact you did that, but I will look at your work, and if you get the answer wrong and you didn't have any supporting work, then you miss most of the points. If you've put this down, it shows me, hey, the antiderivative is right, maybe you just made a mistake plugging in the numbers, then there's that partial credit thing. We'll do one here in a minute where sometimes you have some work to do before you're ready to do the antiderivative. You have to do some algebra, do some simplifying, okay? Well, you don't want to take off the integral symbol till after you've done the antiderivative. So this tells me, okay, I've already done the antiderivative. Now I'm ready to plug in the 3, plug in the 1. So now my work would look like this. 1/3, 3 cubed, minus 3 times 3. Okay, that's the first part. You don't really need parentheses around that first part. That's not as big a deal. But that's the big F of B that I just did right there. Minus, and now I plug in the 1. That needs to have parentheses around it. That's probably the most common mistake people are going to make on these fundamental theorem problems is, just like the quotient rule, you're subtracting and then you're not going to distribute that negative through or you're going to lose track of it here. So I always like to think of big F of B as one thing, big F of A is another thing, work those two separately and then do my subtraction. Okay, so 3 cubed is 27 times a third, that's 9, minus 9. Here we get 1/3. Minus 3, so we end up with 0 minus, what's that, 1/3 minus 9/3, negative 2 2/3 or negative 8/3. If you rather do improper, I like doing improper fractions, rather do mixed numbers is fine, add the opposite, and so we get 8/3. Now, this is a no calculator quiz. Don't make the mistake some of you made in the midterm where you tried to divide it, get a decimal, all that stuff. Just leave it, 8/3, 2 2/3, whatever. Don't compound that and get a wrong answer. Okay? So 8/3 is what you got. Now a problem like that's worth probably 3-4 points. Maybe you get a point for the antiderivative, a point for the answer if it's worth 2. Maybe you get points for several parts of the antiderivative, whatever. So especially when it's no calculator, not a bad idea to show more of your work. Okay, so that's a pretty basic, fundamental antiderivative problem. Now, if you turn in your books real quick to page 333, should be an easy one to remember. Okay, and it is one that we need to remember because, when it comes to the gateway test, you will find that even though some people find antiderivatives more difficult, the list of rules is much shorter. Okay, remember that derivative rule list we have? Of course, you still need to know those. This is your entire list for antiderivatives. Okay? This is your entire list for antiderivatives. However, the difficulty lies in the fact that to be able to do an antiderivative, you have to rearrange or rewrite your function so that it looks like one of those. Those are the basic things we can do antiderivatives of. Those are the ones we'll be responsible for. Okay? Notice there's no cosecant in there and those kind of things. We'll probably stick with just those there. Now remember, when you do an antiderivative, it has to kind of go in reverse. Doesn't mean cosecant doesn't have an antiderivative, it just means we're probably not going to memorize it. Okay? All right, so if we go through the list, for tomorrow, how much do you need to know? Well, you should know just some of the basic ones. Number one, of course this list is supposed to be the basic ones, but we'll just do the basic ones in the list of basic ones. Number one, the power rule. You raise a power up 1, divide by new power. We should do that. Number 2 is probably one you're going to have to try to remind yourself of. The antiderivative of 1 over x is natural log of x. Don't worry about the bars right now. We'll talk about why there's absolute value bars there later. But when you do absolute value or antiderivative 1 over x, it's natural log of x because, number one, the derivative of natural log is 1 over x. And you can't do a power rule if x is negative 1. Because you raise it up to a 0, divide by 0, you can't divide by 0. So you're going to have to remember that one. The third one we should know, e to the x, its own antiderivative. Don't worry about the fourth one right now. That'd be the 2 to the x, 3 to the x, that stuff. Antiderivative of sine is negative cosine. Antiderivative of cosine is sine. Antiderivative of secant squared is tangent. I mean, again, that's basic derivative rule. And then the 2 arcsine and arctangent down there. Probably not going to throw an arcsine or an arctangent at you tomorrow. Okay? So I wouldn't worry too much about that. Another note I would make on page 333 is those last two with the dx on top there of the fraction. I usually don't write them that way. I usually write a 1. The way we remember them on derivatives, I'll write a 1 on top and put the dx out to the side like we normally see the dx. But sometimes they throw it up on top when you have a fraction like that. Don't be bothered by it, but I won't write it that way very often. Okay, so those are some of the basic ones we need to do. Okay, so let's look at this one. Okay, let's say we have the integral. Let's go from 1 to 4 of x squared minus 2 divided by square root of x dx. Okay, so let's say we need to define this definite integral. We need to find this area. Now this is no calculator. I have no idea what that graph would look like, but it's some function. It's got some piece of area from 1 to 4. We cannot do the antiderivative of that. There is no quotient rule for antiderivatives, right? It's not. We don't have this big list of rule for antiderivatives. It's basically the derivatives backwards, and page 333 is your whole list. So what you have to do is you have to take something like this and make it look like, put it into a form that will allow you to use the rules on that page. So anybody have any ideas? Separate. Remember early in the year I said, now you got two options. First of all, we call this x to the 1/2. No matter what we do here, we're going to want to think of that as x to the 1/2. You can bring that x to the 1/2 up on top as a negative 1/2 and distribute through. But I think I told you that's probably not the easier way to do it. And I think I said that there's going to come a time where we're going to split them up. If you got a single denominator, this is that time. This is also where I talked about the importance of that right bracket notation. If I go ahead and split this apart, I want to continue to write my integral symbol because what will happen is you'll get caught up in all the algebra and you'll kind of forget that you haven't done the antiderivative yet. You'll be doing all this algebra and then pretty soon you'll start plugging a 4 and a 1 in and you haven't even done the antiderivative. Okay? So that's kind of your signal that, hey, once I do the antiderivative, I do the right bracket notation. So here I rewrite the integral. I'm going to split it apart, x squared over x to the 1/2. How much of this work you show is up to you. But I'm going to do it just since this is our first one. So I've split that, algebraically, I've split that into 2. Okay? Now I'm going to go ahead and simplify those. So what's this first one here? That's x to the 3/2 minus, and then what about this one? Two x to the negative 1/2. Right? Dx. Okay? So again, all I have done there is algebra. Haven't done anything with fundamental theorem part 2, but now I'm ready. Because now I can use one of those properties we learned in section 1, which is we can split this into 2, do it individually, right? And I won't write them out as 2, but essentially now we can do power rule on both of those. So let's go ahead and do it. What would the power rule be on that one? X to the 5/2 divided by 5/2, which is multiply by 2/5, right? Multiply by the reciprocal. Okay? Minus, here I'm going to raise that up to 1/2, divide by 1/2. Well, divide by 1/2 is times by 2. So yes, you're going to have a little bit of work with fractions possibly. Okay? Don't need the plus c. Put our bracket in, 1 to 4. So the right bracket is a signal that, okay, we've done our antiderivative, that's our big F. Now we're doing big F of B minus big F of A. Now this would be a little more on the difficult side, right? If you have 3 of these tomorrow, 2 would be more like the first one. 1 could be like this one, okay? But it's not that bad. We put our 4 in there, we get 2/5. Again, if you show your work, it helps a little bit. I'm going to put the 4 in. Okay, that's the first part. Minus. Now I'm going to put the 1 in. Like so. Notice the parentheses. I got big F of B minus big F of A. So now how do you do 4 to the 5/2? Bottom number is square root. So square root of 4 is 2, and then 2 to the 5th. What's 2 to the 5th? 32. 32 times 2/5, 64/5. Minus 4 to the 1/2, that's square root, that'd be 2. 2 times 4 is 8. That's that one. Minus 1 to anything is just 1, so that's going to be 2/5 minus, and then that's just 4. So those aren't too bad. This is why I like improper fractions. I think they're easier. 8 would be 40/5, right? 40/5. 64 minus 40 is 24/5. Minus, and this one would be, this would be 20/5. So 2/5 minus 20/5. Negative 18/5. Add the opposite. What? 42/5. And that's reduced. Right? It'll be 8 2/5. Don't be surprised if you have at least one tomorrow where you have some fractions and it's a little bit messy, even though it's no calculator. Okay? So 8 2/5 would be that area. Now there's a lot of stuff going. I mean, if all you messed up was this last part, you got a lot of points for getting to that point, right? Getting the split up, doing a proper antiderivative and so forth. Again, that's a fairly small part of the quiz. 2 to 3 questions most probably doing that kind of thing because we have all this other stuff that we had talked about. Okay? We'll be doing more with antiderivatives later on next week. Okay? But there you go. That's the area. That number is the area under that graph from 1 to 4. All right. Let's do one that has average value real quick. Okay? We had that formula that I had you put in your notes a minute ago. So let's say we said do the average value of sine of x never upgrade when your software is working. Yeah. All right. Is it just full? All right. Find the average value of f of x equals sine x from pi halves to 2 pi. That's the problem. Find the average value. So whenever you have a function and it talks about finding the average value of that function, this kicks in this thought of this formula. Now, the particular formula comes from this, and I showed you this at one day very quickly, but average value comes from the thought that this blue graph right here has a bunch of y values, a bunch of outputs. Surely there's some number that's the average of all of those. How could we calculate that average? Well, it turns out, and it seems to make sense, and we're not going to prove it, but it would seem to make sense that that average value is probably somewhere, oh, say, right about there. Okay? And if you look at that, I think it's reasonable that, yes, this y value would kind of be the average of those blue y values. It also seems reasonable that that blue area is the same as the purple area, right? That seems to be sensible. Well, this blue area, of course, is the definite integral. The purple area is b minus a times the average value. So if you want the average value, you should be able to just take the blue area, divide by the width of the purple, and that should give you the height, right? The blue area is the same as the purple area. That area divided by the width should equal the height, which is the average value. That's where this formula comes from. Okay, so what we're talking about in this problem, not necessary to draw a picture of it, but what we'd be talking about is, it's kind of fun to see if we can kind of estimate. Here's a sine graph. Here's pi halves right here. Here's 2 pi right here. So we'd be talking about these y values from there to there. Now, anybody have a guess what the average, just an estimate, rough estimate, what the average value would be from there to there? What would be the average of the y values from here to there? Negative 1/2, negative 0.3, negative 0.4 I was hearing, right? Somewhere in there, it's going to be negative because there's more of them down here, okay? So something like that might be a reasonable guess. All right, well, let's do it. You wouldn't have to do any of this up here, okay? But just to think it through, that's what's happening. So how do we set it up? According to the formula, the average value would be the integral from pi halves to 2 pi sine x dx 2 pi minus pi halves. That would be the formula. Now, at this point, you've got two different ways to get this because the top part is a definite integral, and as we had up here earlier, we have two different ways to do a definite integral, either geometry or fundamental theorem part 2. This one, there's no geometry under the sine curve that we could use, so this is going to be fundamental theorem. So what's the antiderivative of sine? Negative cosine. Right bracket. We don't need this. Anytime we do fundamental theorem part 2, we don't need the c. We do not need the plus c because when we subtract them, we're just going to subtract the c's out of it. Okay? All right. And then and what's 2 pi minus pi halves? 3 pi halves. So this would be 3 pi. Sometimes we forget the bottom piece, so don't forget that bottom piece. Okay, so that'd be 3 pi halves on the bottom. So here we go. We're going to plug in that. So that'd be negative cosine 2 pi minus negative cosine pi halves. Right? Now minus a negative turns to plus. What's cosine 2 pi? Cosine 2 pi is 1, so this would be negative 1 plus cosine pi halves. Cosine pi halves. 0. So this would be negative 1 over 3 pi halves. So invert that. That'd be negative 2 over 3 pi. Now that's perfectly fine to leave as your answer. Now 3 pi is what, about 9? 3 pi is about 9. So negative 2 over 9, negative 0.2 is what that would be about. Negative 0.2 repeating somewhere in that range. So that wasn't a bad estimate. Negative 0.2, that seems reasonable that that'd be our average value. Okay, so that's just an application of using the definite integral. Just got to know that formula for average value. Okay? All right. That is it as far as what we have to do. I'm going to go ahead and let you work at this point. If you've got some questions to ask me, that'd be great. Here's your homework. In section 5.3, we're going to do the ones. Oh, wait, what about, did some of you have questions about 48?
Yep.
Yeah.
Okay, we'll get to that here in a second. We'll talk about 48. Okay? But here on section 5.3, we've got 19 through 30, which is just some of these fundamental theorem part 2 problems. Okay? Like we've just been working on. What else is on that section that we haven't done yet? That'd be 49. 49, talk about that one. That will not be on the quiz tomorrow. Okay, 49 will not be on the quiz tomorrow. 55 through 58. Okay, so that finishes up section 5.3, and then in the LH packet, page 298, is some more fundamental theorem part 2 practice. 3 through 36, that's multiples of 3. 3 through 36, multiples of 3, so about 12 problems. Okay, so 19 through 30 and the LH, that gives you some of this fundamental theorem part 2, but don't forget to go back and practice the chart and all that other stuff. All right, let's talk about 48. Because something like 48 could be on the quiz. Okay, there'll be a component of the quiz that's just the kind of question you can't really study for other than to just have went through the homework and understand the concepts of what we're talking about. And ask them in a variety of ways, but if you understand the concepts, you should be able to explain or show or whatever. Okay, here's what 48 said. They said if f of a does not equal 0, we're supposed to show that the derivative of the integral, they have an a there I think, little f of t dt, that's the left side, we're supposed to show that that does not equal the integral from a to x, the derivative with respect to t, little f of t, with the dt out here. Right? Did I copy that right? You're supposed to show that if this part is true here, that these two are not equal. Somebody want to take a crack at it? I mean, a couple people in the other class have some good thoughts on this. I don't know. I kind of hold you guys up here, to certain levels. So Tori, go ahead. What's that?
The only thing that I did was like you can simplify the left side, which is like
F of x. Don't forget that. Yeah, this side is the fundamental theorem part 1, right? The left side is verbatim little f of x. That's fundamental theorem part 1. Derivative, because what it's saying is derivative of the antiderivative, right? Okay. What about this side? which is the antiderivative of the derivative, right? So let's think notation here for a minute. In essence, this is saying that if you do the derivative of the antiderivative, that's not the same as doing the antiderivative of the derivative. In other words, they're kind of saying the order matters, right? I mean, that's kind of what this is saying. Well, let's don't think about it notation-wise for a minute. Let's just think about it. Oops. This is ridiculous. Eraser. Well, that was some upgrade.
Color over it white.
Color. That is. It won't even let me. Yeah. Okay, anyway, what could possibly change if you do antiderivative of the derivative versus derivative of the antiderivative?
Plus C.
What about the plus C?
When you do antiderivative of the derivative, there could be a plus C.
Right here, let's think about this. We talked about it a minute ago. If you're starting on the inside, if you do the antiderivative of this, you'll have a plus C. But when you do the derivative, the C goes away. In this case, and I like what somebody said here, I'm going to write that as a matter of fact. Somebody said that this would just be F prime right here.
Don't make a mistake.
Yeah. Somebody said that would just be F prime, and that's right. So here's the derivative, F prime. Then when you do the antiderivative of F prime, what would you get? Little f of x, because that's the antiderivative of this, but when you do the antiderivative, you have a plus c. So when you do the antiderivative last, you get a plus c. When the other way, it disappeared. So that's why they'd be close to being the same thing. It would seem like they would undo each other. They should be the same. They're not quite the same. Now, that's where this little thing comes in right here. F of a cannot equal 0. Now, let's look at this from one other perspective. Think about this new thing we learned with Fundamental Theorem Part 2, because we can actually use that even when there's x's here. We can take this and we can write it using Fundamental Theorem Part 2. We can say, okay, let's do the antiderivative of f prime, which would be what? F, and then plug in an x, so that'd be f of x, minus the antiderivative f, plug in an a. So that f of a, that minus f of a is really your plus c, isn't it? Okay? Well, now you look at this and you look at this. Well, they're not the same unless what? Unless f of a is 0. So that's why they added in that f of a. As long as f of a is not 0, they get this. Now, you wouldn't have had to do that to get points. If I had this one on the quiz and you somehow said, you know, this side's f of x, I might have been worth a little something. But if you talked about how that plus c would make the difference, somehow discuss that. That's a harder one, but, you know, there might be a question or two or something in there where it's not really something you study for, but it's just, hey, if you understand the concepts, you know, think your way through this and be able to explain kind of what's going on. But a lot of it will be chart stuff. I hope you find that easy. Some of the basic antiderivative, you know, some of these things with some practice here, I think you'll be okay with those. You might get into the weeds a little bit with those fractions and stuff, but that can happen. You know, so that's it. I pretty much laid it out for you there when we went through at the beginning all the various things we've done. Okay, so there's your homework up there. You got the rest of the time to work on that. If you've got questions, so these two lines up here, let's get working on it. If you've got questions, let me help you.
Can I go to the restroom?
Yes.
Can I go get a water bottle at my locker?
Everything.